Hey guys, welcome to day 18. We're continuing our discussion of continuity, but today I'm going to approach it a little bit differently because there's not many good examples in the textbooks that I use discussing continuity, and so usually when I teach this in a classroom, I simply work through these problems in class and kind of discuss how to approach various parts of this. So that's what I'm going to do today. I'm going to pull up your homework problems and discuss through some patterns you might notice, as well as one theorem. And that's the only thing we have today in terms of notes is this theorem. But otherwise, this is pretty much it. It'll be a lot of discussion, a lot of talking, so sure, get tired of my voice. But let's see what we can make of this material and see how we can actually come together and understand continuity just a little bit better. First, let's go ahead and talk about our theorem. So for today, the only theorem we have is called Theorem 111. What it states is that you have two pieces. You have to have a real number, which I'm going to call b, and you have to have two functions that are continuous. So f and g are continuous functions at some point c. In this case, c is arbitrary, meaning it could be anywhere, it could act as anything, it could be along the entire spectrum, we don't really know. First thing to note is that there is what's referred to as continuity is maintained in the following four situations. When you have a scalar multiple, such as b times f. In other words, how we should interpret this information, last time we talked about how linear functions are always continuous. Let's make f equal to a linear function x. What this means is that if we take, since we know x is continuous, meaning it has a limit at every point, and the value matches that limit at every point, if f is continuous, then we know, for example, 2x is continuous because it's just a scalar multiple of the original function. So is, negative 3x. So is, 5 pi over 4x. Like, as long as we're multiplying by a real number, as long as we know this one's continuous, then all three of these are continuous. Because again, b is just some number. The second condition is that if you have two of these that are continuous, this is referred to as a sum difference. If we know both f and g are continuous, then if you add them or subtract them, they maintain continuity. So let's assume we have that second equation, g. We talked last time about how quadratics are continuous, so we could say that g is x squared. So if we know x is continuous, if we know x squared is continuous, then we also know, x plus x squared is continuous. We would also know x minus x squared is continuous. And of course the other order too, because g and f are arbitrary. So what this means is, like, basic combinations of all these functions have to also be continuous. Next one's the big one. 3, it's the product. As long as f is continuous and g is continuous, then if you multiply them, they will also be continuous. So if we look back at this example, if we multiply x times x squared, then we also know x cubed is continuous. If you multiply this new one times x or x squared, we can keep building bigger and bigger ones. And so you can see why last time we said that all polynomials are continuous. This is true because if we just know x is continuous, then we can eventually build every other polynomial by adding, subtracting, multiplying bigger and bigger x's, or multiplying by a constant, and then putting them together. And so you eventually can build the entire polynomial set just by knowing that x works. The last one is the tricky one, because it has a condition. The quotient is also true. F divided by g is also continuous. However, at that point, g cannot equal 0. Because if g equals 0, then you can't divide by 0. And so this is a big detail. This is perhaps the most important thing in our notes today and from last time, because we discussed how to use the analytical approach to simplify these. You'll notice that this big one occurs when the bottom is equal to 0. So let's look at now our homework. So these are your homework problems. It says, find the x values, if any, at which x is not continuous. Now what I want you to do is I want you to approach this with the concept of, we know certain functions are continuous. For example, we know all polynomials are continuous. That's the first thing. We know all polynomials. Number 2, we know all trig functions are continuous in their domain. So for example, sine is always continuous because sine has a complete domain. Cosine is continuous because it has a complete domain. And while the others, tangent, cosecant, secant, and cotangent, well, they have pieces of their domain that break down. Everywhere it doesn't break down, it is continuous. And so there's a lot of these that are very straightforward. And note the biggest problem comes from the fourth part of our theorem, if we ever divide by 0. And so you can simplify most of these by asking the question, is there ever a time the denominator equals 0? And if so, what value of x is that? Let's look at our first one. So on 35, when will the denominator ever be equal to 0? Well, first of all, we know the top is fine. It's a 6. 6 is a number, so therefore 6 is continuous. That makes sense. The bottom is x. So according to theorem 1.11.4, fourth property of that 11th theorem, we know from that piece that x is continuous everywhere. And so dividing them should be continuous as long as it never equals 0. Here's the problem. On number 35, it will equal 0 when x equals 0. And so, on 35, the correct solution is, this is an example where x equals 0 is not continuous. And so you could phrase it in a number of different ways when you write it. You can say things like, continuous everywhere except x equals 0. It is discontinuous at 0. It is discontinuous at x equals 0. You have to reference which variable is the problem, which in this case will always be x for the problems you have tonight. And you have to indicate that it is discontinuity you're dealing with, because that's the important thing. You either have to compare it to what is continuous or reference what is not continuous. And so on 35, the answer is x equals 0. Notice the second part, though. Which of the discontinuities are removable? Now remember, removable discontinuities are ones where the top cancels with the bottom, creating something that's removable. Notice that there's no x on top to cancel with the x on bottom, so on 35, there are no removable discontinuities. They are all non-removable. Looking at 36, same concept. The top is always continuous. It's a 3. It's a number. Numbers are continuous. On bottom, that is a linear equation. X minus 2 is a linear equation. Because of that, if I was to investigate where this function breaks down, it actually breaks down at a value of 2. This is because if I have x equals 2 and I plug that into my function, the denominator is equal to 0. And according to theorem 111.4, I can never divide by 0 and maintain continuity. So on 36, the answer is discontinuous at x equals 2. Now, is it removable? No, it is not. That is because on top there is nothing to cancel with the x minus 2. 37 and 38 are both polynomials, so I can actually just say no discontinuities or continuous everywhere, and 37 and 38 are done, because there aren't any points of discontinuity. But 39 does have points of discontinuity. In fact, they occur in 2 places. Take a second, if you're looking at your homework, take a look at those problems, and see if you can figure out where they are. Okay, you should get 2 answers, at positive 2 and at negative 2. How do we find those solutions? Well, it's actually quite simple. In general, one of the things you want to do for these problems is you want to take the denominators. So for example, on 39, I have 1 over 4 minus x squared as my function, f of x. What you want to do is you want to take the denominator portion of this problem, which is just the 4 minus x squared, what you want to do is you're going to take that portion and let it equal 0. So 4 minus x squared equals 0. Then solve. I would add x squared to both sides using algebraic properties. 4 equals x squared. I can then take a square root of both sides, giving me x equals plus or minus 2. So these are the places where we're going to have discontinuity. Note this can only tell me where the discontinuity is because of our theorem here, which states that we're never allowed to have the denominator equal to 0. The denominator cannot equal 0, so how do we find those places? We force the denominator equal to 0 and see what happens. So in this case, there are 2 places, but let's look at the second part. Are these removable? Again, no. These are all non-removable because there is nothing to cancel with the 2 and the negative 2 on top. If I look at 40, I have the function f of x is equal to 1 over x squared plus 1. I then, once again, take that bottom portion, set it equals 0. I'm trying to force the one thing that can't be true, right? I'm never supposed to have it equal to 0, so I force the one thing that can't be equal to 0 to become 0 to try to see when that could happen. Now what happens is I subtract 1 from both sides. I get x squared equals negative 1. I square root both sides, and I get x equals plus or minus I if you take an algebra. This is not a real number anymore, which means that this function is actually continuous. If you actually graph this function, you will see a continuous function. There will be no asymptotes, there will be no jumps, there will be no holes. Let's look at one where we do end up having a removable one. In this case, that is number 43. If you look at 43, we have x over x squared minus x. One of the things you can do is you can factor first. So we have x on top. I factor the bottom into x times x minus 1. And now I can once again choose the bottom portion, set it equals 0. This happens in 2 places, x equals 0 and x equals 1. However, one of these is removable. It turns out because we could have canceled the x's, that makes this top one removable. The bottom one stays non-removable because there's nothing on top to cancel with that thing on bottom. Now, this is one method of doing these problems, and it's not the only method though. Keep in mind, you could have instead graphed each of these functions and manually looked for places of discontinuity. Now, asymptotes and jumps are easy to see. Holes are much harder. Some graphing calculators won't even show them. Like, for example, if you have a TI and you try to showcase where you have these holes in your function, they don't appear. They're not there. They're just not. And so you can't just manually find it. Now you can use the table feature to do some of it, but again, it has limitations. Knowing how to do this analytically and by the theorems is the far superior way because it guarantees accurate results every time. Now, just because there's something on top and something on bottom does not guarantee it's going to end up canceling, but that's why you have to check. Take a look at number 44. We run out of space here. Number 44. On number 44, we have an x on top and an x squared minus 1 on bottom. I would recommend, if possible, to factor first. So on top we get x, on bottom we get x plus 1 and x minus 1. I can then do the same property as I did before, isolate the bottom, set it equal to 0, x plus 1, x minus 1 equal to 0. This will give me 2 solutions, positive 1 and negative 1. But notice neither of these will cancel with the top. Right? There's no x plus 1 on top. There's no x minus 1 on top. So both of these are still non-removable. It's only by canceling algebraically like we did last time that we end up having removable discontinuities. And the rest of the problems, many of them have at least one removable and at least one non-removable. So keep that in mind. The goal of today is to be able to look at a function and ascertain quickly and effectively whether you believe it to be continuous, And Theorem 111 helps with that process because it gives us a concrete understanding of if we know certain functions are continuous, then by definition, other functions are continuous as well. Take a look at number 41, one I intentionally skipped over. Notice that it is 3x minus cosine. Here's the thing. We know x is continuous because it's a linear function. Therefore, according to the scalar multiple part of Theorem 111, 3x is continuous. We know cosine is continuous because it's part of our definition of cosine. Therefore, adding 3x or subtracting 3x with cosine should also, by definition, be continuous. So 41 is continuous everywhere. It has to be, because 3x is continuous and cosine is continuous. In fact, 42 is the same way. There's no places where cosine breaks down, so if I multiply x by a number, cosine's still going to work. It'd only be if we were using tangent that something might go wrong, or sine, or not sine, cosecant or secant, any of those weird ones, where something could go wrong because there are places where they don't maintain continuity across the entire domain. So, the big part of today is being able to still maintain your factoring skills from last time, so using analytical approaches to determine whether or not this is going to actually work, but also being able to determine visually, are they removable or not removable, just by looking at the formula. And again, if you can factor it, you can determine that easily. Look to the denominator to answer that question. Look at the bottom of your fraction to answer where is discontinuity. Look to the top to see if anything cancels, to look to see if it's removable or not removable. One more time. Denominator dictates continuity, but the top, the numerator, dictates the type of continuity. Is it removable because they cancel? Is it non-removable because they don't? That is it for today. Relatively short lesson. Big pieces at play here. This should be a relatively quick assignment because you can actually graph all of these in theory and quickly get to the solutions as long as you're good with your visual skills. I would encourage you as much as possible to approach it with the algebraic sense first and use the graph to verify if necessary. But otherwise, that is it for today. I apologize for going over so many times the last couple days, and I'll leave you guys with these ones here with some of the answers already given. So that will be it for today. I look forward to seeing you guys tomorrow. We'll continue our last piece of continuity, and I'll talk to you then.